Today in this video, I will be going to discuss about the basic understanding of AI, machine learning, and deep learning. So, what is AI? We say AI. In AI, we give intelligence to the machines. There can be two ideas of AI. One is narrow artificial intelligence, and second is artificial general intelligence, NAI, and this is AGI. These are the two ideas of artificial intelligence. In narrow artificial intelligence, what we say, when we are developing an AI application that performs specific task, some particular task, like I have self-driving car. It is only purpose is to drive a car. We are building an application for that. Or smart speakers. They come under the idea of artificial narrow intelligence. Artificial narrow intelligence. Now, there is another concept I have already told you, that artificial general intelligence. When we are trying to build a system that performs functions that a human can do, or more than that a human can do, we say we are going to the idea of a artificial general intelligence. Okay? Now, this was the basic thing about the AI. The goal of this video series is to go for to give you the understanding of deep learning. So this was the basic understanding of our AI. So if I will say in terms of Venn diagram, I have AI is the superset of both machine learning as well as deep learning. And whatever we do, whether we'll do machine learning, whether we'll do deep learning, the end product is the AI application. End product is the AI application. That means whatever we do, our goal is to build an AI application. So the next thing is machine learning. We say machine learning is a subset of AI. It's a tool. It's a subset of AI. It is a tool for building AI applications. We say it is a tool that allows us to build statistical models of a given data set. Now, there are different types or approaches of machine learning. One approach is we say supervised learning. Second, we say unsupervised. Third, we say semi-supervised learning. Now, as you must all know that in supervised, what is supervised learning? In supervised learning, we have given data plus label. That means we have given labeled data in supervised learning. And unsupervised learning, examples of supervised learning algorithms are basically, we are saying that classification problem, and second is regression. These both come under supervised learning. Second is unsupervised learning. In unsupervised learning, these are the approaches of machine learning. In unsupervised learning, what we have given? We have given unlabeled data. So in this type of learning, what we try to do, we try to group the data, or we try to cluster the data. Clustering is done. And the third type of data is semi-supervised learning. In semi-supervised, we have given both labeled as well as unlabeled data. Google Photos is an example of using semi-supervised approach. Okay. So the third concept comes is the deep learning. See, we say deep learning is a subset of machine learning. Deep learning is a subset of machine learning. So what is this deep learning? What is this term deep learning? Usually scientists try to find out whether we can build a machine that can think like we humans think. So they came out with an idea of deep learning. Deep learning is simply a term is used when we have deep neural networks. When we have deep neural networks, the core idea behind deep learning is the usage of these neural networks, artificial neural networks, ANN. When we have deep neural networks, when we have deep ANN, we say this is a deep neural network. This is a network of many artificial neural networks, or we can say deep stacked hidden layers are there in deep neural network. Now, before going to the deep into the DL, we will first see the core concept behind deep neural network, that is artificial neural network. What is artificial neural network and how it works? We're going to see that. We'll be going to see that. Now, artificial neural network, ANN. artificial neural network were inspired by the biological neurons of humans. These are inspired by the biological neurons of humans. So, I will simply take one example and I will show you that how this artificial neural network works. Simple example I will show you to explain you how artificial neural network works. In artificial neural network, I have something known as an input layer. I have something known as an hidden layer, and I have something known as an output layer. Now, the purpose of this input layer is to pass input to the hidden layer. Input to the hidden layer. Suppose I have a features x1, x2 and x3. So I will pass these features to x1 to neuron first, x2 and x3 as an input to the hidden layer. Every neuron of the input will be connected to the hidden layer, and then later this hidden layer will be connected to the output layer, and after that this will be the output layer. This is known as input layer, this is known as output layer, sorry, this is known as hidden layer. I can say this is hidden layer 1 and this is known as output layer. I can have as many as hidden layers in the neural network. Likewise, I can have as many as neurons in the hidden layer. I am showing only one here because I am going to explain you how this artificial neural network works. See, if I will see you, what type of neural network is this? We say this is a two-layer neural network. Two-layer neural network. Always. We say, sir, we have an input layer here, but we don't consider it in terms of an architecture definition. We say input layer is not considered when we give the definition architecture of a neural network. So we say neural network, this is a two-layer neural network, simply. Now, see what is going here in the neural network. You see, every input layer is associated with the features, with the weights. We say every input feature is associated with the weights. And you don't need to worry about what these weights are, how are they initialized. I'm going to explain all these things in the coming videos. What are the weights, what are various techniques for initializing these weights. Okay, now every feature is associated with the weight. See, x1 w1, x2 w2, x3 w3, every feature. What this weight specifies? This weight tells us the importance of the feature in predicting the output. So, when Now we have this hidden layer. You see here, input is passed to the hidden layer. We did this associated weights. What is the process that is happening here? In hidden layer, actually two things happen. First thing is this, that I say two things happen here in the hidden layer. First thing is that this W1 is multiplied with this, with its associated feature. Likewise, with its associated feature, and then the summation of these is taken. This is the first operation. Summation of this is taken. So we can write this as summation of Wi xi, where I running from 1 to n. Okay, and at the top of this, some bias value is added. B1, suppose it is B1 bias value, and you don't need to worry what this bias is. Okay, I'm going to explain this why we are adding this bias. See, I have told you that we are randomly initializing these weights. It may be happen sometimes while initializing. It may be happen sometimes while initializing this weight. These weights will be initialized by default to 0. Okay, these weights will be initialized by default to 0. When we will initialize these weights to 0, what will happen? You see here what will happen. This all will become 0, and the information processed from here to this hidden unit to another hidden unit will be 0. There will be no change. So in order to overcome that problem, what we do, we add a bias value, and we usually say that bias, we never give 0 to this bias value. Always remember this thing, never give 0 to this bias value. Okay, so this is the main purpose of adding this bias value here. Now, after this operation is over here, suppose we have calculated that value is equal to y, and on the top of this we apply an activation function. What we apply? We apply activation function on this value. What we apply? An activation function on this value. There can be many activation functions are there, like we have sigmoid activation function, second is ReLU activation function, and third one is tanh. So we can use any of these functions in this layer. You don't need to worry about what is this sigmoid function, what is this ReLU function, what is this tanh function. All I'm going to explain in the upcoming videos. I'm going to explain all this in the upcoming videos, and when to use which activation function, that will be covered in the upcoming videos. The only thing you have to remember here, that here two operations are performed. First operation is that we take summation of input future times it is associated weight, and then the activation function is applied, and these all things happen within this hidden unit. Two things: one is taking the summation of input weight time is input, wait time is input, and after that applying an activation function. This activation function can be any activation function. It can be tanh, it can be sigmoid, or it can be ReLU activation function. Okay. After that, this value is passed to this unit, and weight is multiplied here. Again, same thing happens in here. Same two operations. First, weight is multiplied with the input, and after that activation function is applied and the output is calculated. Y hat is calculated here, and this whole process from input to output, this whole process from input to output is known as forward propagation. Forward propagation. So I will give an example, and with the help of that I will try to explain you what is this forward propagation, what is the purpose of this forward propagation. See, if you can see here, I have neural network 1, 2 and 3 input features, and I have a hidden layer 1, and I have a output layer. Okay, see if you can see here, I have x1, I have x2, and I have x3, x1, x2 and x3. If I have the weight of w1, w3. Suppose I have the features for x1, I have the features for x1. Suppose I have features for this. I can take the example for features. I have, since I have calculated this, and okay, suppose I will take the values for x. I will take the values for x. 1 I will take 4, and I will take 6 for x2 and x3, and for the weights I will take for w1, I will say this is 4, this is 6, and this is 3. And for w1, what I will take the value for w1, I will take the value 0.1, and for w2 I will take the value for 0.2, and for w3 I will take the value for w3 I will take 0.3. 0.3. Simple. Now what I will do, these values will be passed to this hidden layer, and here first thing will, and bias of 0.1. Okay. Now first thing what will happen here, first thing will happen that we'll do one thing, we'll do 4 into 0.1 plus 6 into 0.2 plus 3 into 0.3. What will be this value? Plus 0.1. First operation will happen here. What will be its value? You see, its value will be equal to 2.9. Okay. That is, we calculated this value, and this will equal to, suppose it be z equal to 2.9. Okay, now its value z will be equal to 2. Second step, what we have to do, suppose I will use an activation function of sigmoid. Suppose I will use the activation function of sigmoid. What is that? Its value. Okay, its value, you don't need to worry about sigmoid functions. In the next video I will be going, in the next video I will be going to discuss about activation function, different activation functions, their mathematical formulas and something like that. So we have activation function of sigmoid is equal to 1 e raised to power minus y. Okay, so what will I do? I will do write it minus 2.9. Suppose this value is equal to 0.3. Suppose I am supposing. Suppose this value equal to 0.3. So what will happen? 0.9. Okay, suppose this value will be equal to 0.3 and this value will be positive to here, and here again weight is applied. Suppose this weight is 0.1 into 0.3. What is that? What is that weight equal to? 0.1 into 0.3 is equal to how much? 0.3. Okay, is it okay? Or it is, you see, can anybody tell me? I think it is equal to this. Okay, now my concern is that when I am applying this value 0.3 here. Now suppose I get the value here of 0.4, something like that. Suppose I get the value here 0.4 as y predict. Suppose I get the value 0.4 here as y cap. Now you see here, if I will get the value 0.4 here, you see what will happen. I have the feature, I have 4, 6, 3 and output we have 1. Now if I will be using binary classification, in binary classification what we usually do, if this value is more than 0.5 or equal to 5, we take it as n1, and if it is more than less than 0.5, we take it as 0 in case of binary classification. So what will be the value of output y hat? Well, that will be equal to 1. Sorry, 0, because this is less than 0.4. Now see here what will happen here. When we will say that our predicted value is 1.4, okay, but 0.4, sorry, but our actual value you see is 1. Our main aim is to get the predicted value almost equal to 1. Our main aim is that we should get a predicted value almost equal to 1. So how we'll do that? So one is, we have seen this y cap, we define a loss function. We define a loss function. Same thing here. We have different loss functions. I will be showing you here one loss function, 1 minus y cap cos cap, and this is known as mean squared loss. Okay, I'll be using this loss function here. See, what can I do? What I simply do, I will put the values here. I will do 1 y minus y cap cos square equal to 1 of 0.5 cos square. What is that? 1 minus 0.4. That is 0.6 cos square. Okay, what is that value? That is 36. This is 0.36 by 2. That value is equal to, loss is calculated, that loss value will be equal to 0.18. That loss value will be equal to 0.18. Okay, now you see here loss value is calculated. Now our main aim is that we should get y predicted almost equal to y trust value. Okay, so what we do, we define a loss function, and after defining a loss function, we try to our main aim is this. Now here what we do when we calculate a loss function, and you see the smaller the loss function, the more the predicted value be the close to the truth value, and the larger the loss function, the more far will be the predicted value to the actual value. So main concept is here to reduce, we have to reduce this loss function, loss value. So how can we reduce this loss value? We can reduce this loss value by applying a back propagation. And you see what is this by applying a back propagation. In back propagation we have techniques, different techniques. We have a technique Adam. We have different techniques, like we have gradient descent. Okay, these are known as these we have optimizers. So if anybody tells you what is the purpose of optimizer, you have to say that its function is to reduce this loss function. Optimizer's function is to reduce this loss function. And likewise, don't need to worry about what is this ADA, what is this gradient descent, what are the all optimizers. I'm going to explain you in the next coming videos different optimizers, and most common optimizer we use it ADA. So how this back propagation works? Simply what we do in the back propagation, we update these weights and the bias value. What we do, we update bias and the weights in the back propagation in order to reduce the loss value. Okay, so there's a how we do that. There's a formula for weight updation and likewise bias updation. Suppose formula for weight updation is W new equal to W old minus learning rate of derivative of loss with respect to derivative of W old. Derivative of W old. This symbol is learning rate, and this is the partial derivative. This is partial derivative. Okay, this we calculate by using chain rule, and that will be discussed in tomorrow's video how this partial derivative is calculated. Okay, go. Now what you understand, first thing, we get an output value through forward propagation, and the backward propagation what happens, weight updation is done, bias is done, and one forward and one backward. This completes one iteration. This completes one iteration. Okay, see now, suppose simple idea. suppose I have, you can see here, suppose I have an input layer, simple. I have a hidden layer and I have output layer. Okay, in the hidden layer I have feature x1, here I have weight associated here, W2, and here is output. And base is also. Okay, now see what is going on. Suppose I will be using gradient descent in propagation, gradient descent in back propagation. So what will happen here? See, I have a weight updation formula. Suppose I have to first what I have to calculate. I have to calculate this weight update. I have to do weight updation of this. Then I have to do this. Okay, this is done through zero. No, see now. Suppose I have W2 equal to W2 minus the learning rate of derivative of loss divided by derivative of W2. Is it? Okay. Now you see here, if I will be using the gradient descent, what I will do, this is my loss and this is the value for W. This is, now you remember this weight updation formula. Okay, see, I will draw this here so that you can get the idea. Suppose I have like this is loss and this is W, and gradient descent curve with respect to loss is like this. Now you see here, what is the weight updation formula? It is W new equal to W old minus learning rate of derivative of loss divided by derivative of, what is this derivative? This is simply a slope. This is simply a slope. We are calculating a slope here. Okay, see, if I have value, I have calculated loss value here. First thing what I will do, I will draw a tangent to this. See, I will draw a tangent to this. See, when you will see the right hand side of this tangent pointing towards downwards, we say that the slope is negative. We say that the slope is negative. What does this mean? That means if the slope is negative, that means this value will become negative. You see, if the slope will be negative, what does mean? We have weight updation formula, learning rate, derivative of loss with respect to the derivative of old. Okay, see, if this value will become, slope will become negative. What does that mean? W old minus, this is, and minus plus learning rate of something negative value. Okay, what does that mean? That means W new is always greater than W old. So if we have a W old here, what I have to do? I have to increase the value of W new. So the next value will be here. Likewise, the next value will be here. The value will be here until we reach this point when the slope becomes 0. When slope becomes 0, this will become 0, and we will see W new. The training will stop here. And this point here is known as global minima. Likewise, when we have a like this here, You see, whenever the tangent, the right hand side of a tangent is pointing upwards, we say that the slope is positive. Slope is positive. So what we have to do when slope is positive? You see here what we have to do when slope is positive. W new equal to W old minus, and this is positive, and this will become W old minus. That means W new will be, what will be that? It will be the less than W old will be the less than W old. If W old is here, suppose, so next value we have to take this. Next, likewise this, likewise this, likewise, until we reach at global minima, when W nil will be almost equal to the W old. And in the real life scenario, this slope never becomes to zero because we have numerous features. Okay, it tends to be zero, but not zero exactly in the real life scenario. This was all about the introduction to the neural networks, and I gave a brief idea of AI, and after that I gave a brief idea of machine learning. Now this was the introduction concept. This video gives the terminology that we use in deep learning or neural networks. See, in deep learning what we have, we have different approaches. Suppose we have ANN is one approach, second approach is CNN, and third approach is RNN. Whenever we have a numeric data, we use ANN, and whenever we have a image data, we use CNN, and whenever we have some time series data, we use RNN. Even we can use CNN, combination of both CNN and RNN, combination hybrid models we use. These are the basic terms that we use in deep learning. Okay, so in the next video I'll be going to discuss how the chain rule works, how propagation calculates, that updates the weights and all that. In the next video I will be going further. Okay.